We have spent several videos building vector spaces, subspaces, bases, and dimension. Now we finally talk about functions between vector spaces. Not arbitrary chaotic functions. Linear maps. Functions with manners. A linear map from vector spaces U to V is a function t from U to V that respects addition and scalar multiplication. Respecting addition means t of U plus V equals t of U plus t of V. Respecting scalar multiplication means t of lambda U equals lambda times t of U. The map is allowed to move vectors around, but it is not allowed to betray the vector space operations. Basic loyalty. Somehow a theorem now. Usually we combine the two rules into one line. For scalars a and b, t of a u plus bv must equal a t of u plus bt of v. This single formula packages additivity and homogeneity together. Mathematicians love packaging things, mostly so they can unpack them later and call it a proof. First example, differentiation on polynomial spaces. Let D send each polynomial to its derivative. For instance, if p of x equals x cubed plus 2x, then dp equals 3x squared plus 2. Differentiation is linear because the derivative of a sum is the sum of the derivatives. And constants pull out. Calculus has been quietly doing linear algebra this whole time. Naturally, it did not file a report. Second example, evaluation at 0. The map E0 takes a polynomial and returns its value at 0. So if p of x equals 5x squared minus 3x plus 7, E0 of p is 7. This is linear because evaluating a sum gives the sum of the evaluations. And evaluating a scaled polynomial scales the value. Third example, integration is also a linear map. The map I takes a continuous function on the interval from 0 to 1 and returns its integral. Because integrals distribute over sums and constants factor out, I is linear. So yes, differentiation, evaluation, and integration are all linear maps. The examples were hiding in plain sight, like math enjoys doing. Now a non-example, because definitions are useless unless they reject something. The function q of x equals x squared is not linear. For example, q of 1 plus 1 is 4, but q of 1 plus q of 1 is 2. 4 is not 2. A bold observation, but apparently necessary. Now suppose S and T are linear maps from U to V. We can add them pointwise. Define S plus T by sending U to S of U plus T of U. To check linearity, feed it AU plus BV. Use the definition of S plus T, then use linearity of S and linearity of T. After collecting terms, we get exactly A times S plus T of U plus B times S plus T of V. So the sum is linear. We can also multiply a linear map by a scalar. Define CT by sending U to C times T of U. Again, feed it AU plus BV and use linearity of T. The result has the right form. So scalar multiples of linear maps are still linear. Astounding that operations behave when defined sensibly. Composition also preserves linearity, as long as the domains and codomains match. If S maps U to V and T maps V to W, then T composed with S maps U to W. The composition sends U to T of S of U. Linearity follows by applying S first, then applying T. Each map respects linear combinations, so the composition does too. In other words, if each machine respects the vector space structure, then chaining the machines together also respects it. Machines, briefly, being more reliable than people. Now we name the collection of all linear maps from U to V. We write L of U, V for the set of all linear maps from U to V. We add maps pointwise and we scale maps pointwise. Because addition and scalar multiplication keep us inside the collection of linear maps, L of U, V is itself a vector space. So linear maps are not just tools between vector spaces. They form a vector space of their own. Mathematics loves building a new house out of the bricks it just defined. Let us summarize before the notation discovers another operation. A linear map respects addition and scalar multiplication. Differentiation, evaluation, and integration give natural examples. Linear maps remain linear after addition, scalar multiplication, and composition. And the collection of linear maps from U to V is a vector space. Next time, we start studying these maps seriously.